Okay, I see we're on. First of all, are there any questions? Homework 2 okay? Straightforward, right? Okay. So I'll try and give you some more challenging homeworks eventually, but so far it's been easy. As far as the homework 1 that was handed in, a couple of comments. Let's see, for some reason, I'm not sure what it is, but you had to calculate the Erlang-C formula in there. And there was a way to do that in terms of the Erlang-B. I guess this was it. And then you had to use that in some other formula, which was something like this. You had the Erlang-C and then t and e to the minus something with a t in it, something like that. Now, what people did was they wrote columns with numbers, but the numbers were okay up to a point, and then they started getting random. I mean, you couldn't tell that, but I could tell it because I would compare what I think is the correct answer with what you wrote down. And obviously what happened was this. I looked back and I saw this. What people did was things like you wrote a program to calculate the Erlang-B, and then you calculated the Erlang-C by hand from this rather than putting that in as part of the program. So that meant that you truncated. And then what people did to make it even worse, didn't make any sense to me at all, was they took this formula and they put in the Erlang-C value by hand, and then they calculated the rest of it and multiplied things out. Now, you already have a program that's calculating the Erlang-B. With one more instruction, you calculate the Erlang-C, and with one more instruction, you calculate this function. And after that, and what that means then is not only is it a lot faster, but it's more accurate, because whatever value the Erlang-C has, however many digits the computer carries, which is zillions, then all of those go into the calculation. So the round-off error, the truncation error, is at the end of 10, 20, 30 digits or something like that, rather than carrying an error through, because when you did it by hand, you rounded this off. So in the future, when I look for, when I ask you to compute something theoretically, I want you to make sure that all the digits that you write down, however many you write, are accurate. You don't want to publish something in which there's a string of digits which are accurate up to a point, and then after that they're random, but no one who reads the figure knows where that point is. I mean, a physicist would not publish something that represents a measurement that goes on for zillions of digits when only the first 2 digits have any significance. So whatever your calculation is, if you present 6 digits, then those 6 digits ought to be all right. If you present 20 digits, then the 20 digits should all be correct. There shouldn't be some random point which the reader doesn't know about, where all of a sudden the correctness ends, and after that it's all, for all practical purposes, random. And one way to make your figures as accurate as possible is to, in a formula, calculate everything out as accurately as possible, because as soon as you truncate something to 6 digits, then everything that's longer than that is just random noise. And furthermore, it doesn't make any sense whatever to do something by hand if you already have a computer that's computed part of it. That just blows my mind that people do that, but it happens all the time, especially among computer science majors. You have to tell computer science majors, never ceases to amaze me, that here's the calculation, by the way, use a computer. If you tell them to use a computer, then they use a computer. But if you just ask them to make a calculation, it seems never to cross their mind that one way to make a calculation is to use a computer. I just don't understand that. Okay, another thing has to do with the curves. Some people made this mistake. I didn't take any points off of these things, by the way. I took off points only for things that were actually incorrect, like writing the simulation code incorrectly. But let's say that here's the code for, or here's the theoretical curve for some function. Now, what some people did was I asked them to simulate certain values and to put those on the graph. So let's say that the values you got were here and here and here and here, say. And by the way, these simulated values and the theoretical values were extremely close. So this shows the high reliability of this kind of argument. All right, now what some people did was in the plotting of this curve, you also had to give certain numerical values. So what they would tend to do is they would give a value calculated at that value, and at that value, and at that value, and at that value, which is okay. But then either they indicated those values, which shouldn't be on their part, because that's not part of the theoretical calculation. The theoretical calculation is a smooth curve for all values, not just for the specific one that you use for plotting. And the second thing is that some people not only just plotted those values, but then they connected them by straight lines, which is, I guess, is close enough for all practical purposes, but that's not the point. One curve is a theory curve, which is smooth, and in effect has no points in it. Whatever points were used for the calculation, either by hand or by the computer, or you keep to yourself. It's a smooth curve that represents the whole function, and then the place where you show the points is at the simulated values. So remember that for future cases. Anything else? Any questions about this? Anything else I can tell you? Okay, let me erase this, and then let's start or continue with where we were last time. Last time we were talking about transforms, in particular Laplace-Dieltjes transforms. But before I go back into that, I want to step back to stuff that was in chapter number 2, which was covered in the earlier course. Actually, I don't really remember whether it was covered in the earlier course, because in the earlier course we actually don't need it. So it's a tool that you could dispense with up to this point, but now we really need it. So what I'm looking at starts on page 26, section 2.4, called probability generating functions. So 2.4, probability generating functions. And these are transforms. The Laplace-Dieltjes transform is simply a generalization of the probability generating function. And what a transform does is it takes information that's in one form and it turns it into another form, and there should be some advantage to doing that. That's why you do it. Now, what these functions do is they generate the probabilities. Okay, so here's the definition. Suppose that we have a random variable, and this random variable is non-negative integer valued. Non-negative integer valued. What that means is that the random variable takes the values 0, 1, 2, 3, and so forth. So let's call a random variable k that's what was used in the book. So if it's a non-negative integer valued random variable, that means that the probability that k equals j is defined for j equals 0, 1, 2, and so on. And let's call that probability, to save writing things, let's call that little piece of j. Now in queuing theory, you're often interested in random variables that are non-negative integer valued, because the j, for example, typically represents the number of customers in the system. So we're going to simply talk about random variables that take on the values 0, 1, 2, 3 with these probabilities. And then we can define the probability generating function as follows. I'll use a notation little g of z. And by definition, it's p0 z to the 0 plus p1 z to the 1 plus p2 z squared plus p3 z cubed, and so on. Now the z is a dummy variable. The z doesn't have any particular significance. And what this thing says is that if you told me what this generating function was, then if I were to expand that in a power series, then the probabilities would be the coefficients in the power series. So if you tell me the p's, then of course I can tell you what g is. Now, if the p's happen to have a nice formula, as we'll see shortly, then often this infinite sum can be summed, and so you get the answer in terms of a nice little formula which has z in it. Conversely, although this is now involves theorems that are beyond the scope or outside the scope of this course, that if I have a function g of z that meets certain requirements, then there is a unique power series expansion. And so if I can find the expansion, then I can pick off the coefficients and I know what the probabilities are. So in effect, what I do is I change a sequence of these numbers, potentially infinite number of numbers, into a single function. And then I manipulate the function, and somehow or other I get the answer back because the information is contained in that function. It's just changed its form. OK, I'll give you some examples. Now, notice that, well, let's see, what are the properties here? One property is that g of 1 is equal to 1. Because if I plug in z equals 1, then I simply get the sum of all the probabilities. And another is that g of 0 is equal to p0. Now, since the p's, notice that the p's are all non-negative numbers between 0 and 1. So if I had a series in which the coefficients of the z's were all 1, then this would be the standard geometric series, and it would converge as long as the absolute value of z is less than 1. So that means that if the p's are non-negative numbers whose sum is 1, so each of them is less than 1, then this, in a sense, converges faster than the ordinary geometric series, which means that as long as I'm inside the unit disk, as long as the absolute value of z is less than 1, then this converges and has all the nice properties. This is what everything here is well behaved. So every operation that you might want to perform on an infinite series that makes sense, that works for finite series, will also work for the infinite series, because you don't have any bizarre oscillations or strange coefficients of strange kinds of convergence. So all of the problems of analysis that would come about if we were doing a theoretical study of these kinds of series go away because we don't even consider that, we don't have to worry about them. So if we want to differentiate things, we differentiate, no problem. In particular, suppose that I calculated the derivative of this generating function, because I can do it term by term. That's my argument here. So if I differentiate it term by term, then what you see that what I would get would be 1 times p1 plus 2 p2 z to the 1 plus 3 p3 z to the 2, and so on. And then if I set z equal to 1, then this would simply be the summation of j pj over all j, which of course you recognize as the expected value of the random variable whose generating function we're differentiating. So if I have a non-negative integer-valued random variable and I know its generating function, then I can find the expected value of that random variable by differentiating the generating function and setting z equal to 1. Similarly, if I differentiated this again, then what I would get would correspond to a second moment and a third moment. So we'll see that shortly. So that, in fact, if I have the generating function, I can calculate all the moments of the random variable that it generates by simply differentiating. And sometimes what happens is, in the more, other than the most elementary cases, is I don't actually know what the generating function is, but I have equations that determine the generating function. And so instead of finding the generating function explicitly and then differentiating it to get the mean, for example, I can differentiate implicitly in the equation, set z equal to 1, and then get some other equations which are generally easier, which I can solve algebraically directly for the mean. So we'll see that what happens here is that by making things harder, by introducing this new concept, we actually then make things easier because we've got all kinds of tricks that we can play now. All right, so let me give a couple of examples of generating functions. The first one is for the Bernoulli random variable. Okay, so here's an example. Of course, these are the most trivial examples starting out. Suppose I have a random variable x, and I say the probability that x equals 0 is q, and the probability that x equals 1 is equal to p. And of course, p will be equal to 1 minus q. So this is the typical Bernoulli variable. I have two possible values, which I usually call success and denote by a 1, and failure, which I denote by a 0. And the probability of success is p, probability of failure is q. So what would be the generating function of that random variable? And the answer is, well, what I would do is I would take the p0, which is q. Okay, that's this term right here. So here's the p0, z to the 0. p1 is little p. There's the z to the 1. And that ends because all the other probabilities in the expansion are 0. So this thing over here is the generating function of the Bernoulli random variable. Now, if someone gave me this function, then I could immediately recognize that it generates the Bernoulli random variable because I know that this is the probability that the random variable takes a value 0, and that's the probability it takes a value 1, and all other probabilities are 0. If I wanted to calculate the expected value, which of course we know that the expected value of such a random variable is p, then all I would do would be to differentiate this and set z equal to 1. When I differentiate it, I get simply p, and setting z equal to 1, well, the z is already gone, and so there's my answer. So that's the expected value. All right, let me give another example. Take the case of the Poisson random variable. So here's another example. Suppose that the probability that x, in the book I may have called it by some other name. I keep on changing my mind as to what the name should be, x, k, but I think in context here it's all clear. Okay, suppose the probability that x is equal to j is given by a to the j over j factorial e to the minus a for j equals 0, 1, 2, and so on. In other words, that is, x is distributed as a Poisson variable, and the expected value of x is equal to a. We already know that. Okay, now suppose I wanted to find the generating function of x. So by definition, the generating function would be obtained by taking the probability that x equals j, multiplying by z to the j, and summing over all j from 0 to infinity. That's the definition. So now we just plug in the particular form of the probability, which is the Poisson probability. So what I would have is a to the j over j factorial e to the minus a. That's this part, times z to the j, summed as j runs from 0 to infinity. Okay, now what's going to be the important point here is that for this particular case, and for lots of cases where you have a nice formula for the probabilities, that you can actually sum the series. So the way I do that is I take the e to the minus a outside the summation sign, and then I take the sum, and I combine the a to the j with the z to the j, so I get az to the j over j factorial as j runs from 0 to infinity. And then I recognize this piece right here as the expansion of e to the az. That's e to the az. So in other words, e to the minus a 1 minus z is the generating function of a Poisson variable. Okay, so if I had some problem and I had it represented in terms of the generating function, and then it turned out that that was the answer, then I would know that the random variable that I'm talking about is a Poisson variable whose expected value is a. In fact, to see that its expected value is a, let's calculate g prime of 1. Well, let me calculate g prime of z first. So first I differentiate this. Actually, it's easy to differentiate in this format. So I notice when I differentiate with respect to z, I get a times the original thing, which was e to the minus a times 1 minus z. And then I set z equal to 1, and I find that g prime of 1, well, when I set z equal to 1, the exponent becomes 0, and I'm left with simply a, which just confirms what we already knew, that a random variable who has this generating function has as its expected value a. Now, in elementary books, what they often do, which is really overkill, although maybe that's the way of teaching this, is to take various different random variables and find their moments, for example, by finding the generating function and then differentiating it. But ordinarily, there's no point in doing that. If you have an explicit form for the random variable, then you don't need to go through the generating function. The point is that there are some other uses of the generating function other than simply calculating expected values that make this worthwhile. Notice, of course, again, that if I plugged in z equals 1, I'd get e to the minus 0, which is 1, which says that the probabilities must sum to 1. G of 1 equals 1. Okay, if I plugged in z equals 0, I would get e to the minus a, and e to the minus a is, in fact, the 0th probability. If I say j equal to 0, I would get e to the minus a. So this is, agrees with the properties that I mentioned earlier. Okay, now let's look at something else. Okay, suppose x1 and x2 are independent and let's see, non-negative integer valued. I'll just write that as non-negative integer random variables. In other words, they have generating functions. Okay, so the generating function of x1, and often I'll denote it this way. Generating function of x1 would be the sum of the probabilities. Now, yeah, okay. The sum of the probabilities. X1 is equal to j, z to the j. And of course, the generating function of x2 would be the sum of the probabilities x2 is equal to j, sum z to the j. I should put a z in here. Okay, so the question, what is PGF, probability generating function, sometimes written little PGF, sometimes with periods, sometimes without periods. Okay, what is PGF of the sum x1 plus x2? Okay, and the answer is the generating function of x1 plus x2 is equal to the product of the generating function of x1 times the generating function of x2. So if I want to add up random variables, I have this complicated operation called convolution, which we'll get to in a moment. But I can replace convolution in the formalism of the original random variables in terms of multiplication, in terms of their generating function. Multiplication, of course, is much easier. So in fact, let's calculate the convolution. Okay, to simplify my notation, why don't I say that let the probability that x1 is equal to j be a sub j, and the probability that x2 is equal to k, let's say, is equal to b sub k. Okay, so my random variable x1 has probabilities a0, a1, a2, a3, and my random variable x2 has probabilities b0, b1, b2, and so forth. Okay, so what I'm going to do is I'm going to multiply the generating function for x1 times the generating function for x2. So that means if I were to write everything out, the generating function for x1 is a0 plus a1 z to the 1. Maybe I could recognize this as a0 z to the 0. I think I'll write it that way. a0 z to the 0 plus a1 z to the 1 plus a2 z to the 2 and so forth times b0 z to the 0 plus b1 z to the 1 plus b2 z to the 2 and so on like that. So that's the product of those two generating functions. All right, now I do the obvious, which is I multiply out term by term and collect the coefficients of the various values of z. So to get the coefficient of z to the 0, obviously that's equal to a0, b0, z to the 0. Okay, so I multiply that term times that term, and I have one term that corresponds to the z to the 0. Okay, what about the coefficient of z to the 1? Well, a0 times b1 plus a1 times b0 will give me the coefficient of z to the 1. So I'll write that as a0 b1 plus a1 b0 times z to the 1. All right, what about all the terms that correspond to z to the 2? Well, a0 times b2 plus a1 times b1 plus a2 times b0, z to the 2, and so on. Okay, the next term is going to be a0 b3 plus a1 b2 plus a2 b1 plus a3 b0 z to the 3, and so on like that. Okay, so in general, what I'm going to get is this. Multiplying the term z to the j, I'm going to have the summation of a sub I b sub j minus I as I runs from 0 to j. That's the thing that multiplies z to the j. And then, of course, I have all of that summed over all j from 0 to infinity. Okay, and now I recognize what is this piece right here. Well, that's just the convolution. That's just the sum as I runs from 0 to j of the probability that x1 equals I times the probability that x2 is equal to j minus I, which is the same thing as the probability that x1 plus x2 adds up to j. So if x1 and x2 are independent, then the product of their generating functions generates a series, gives me a series whose coefficients are the probabilities associated with the sum of the random variables. Okay, so what we had here is we have x1 and x2 are independent non-negative integer-valued random variables. So I multiply the generating function for x1 times the generating function for x2, and then I just do some arithmetic on the terms, collect everything, and I find out that the result is something of the form sum of x z to the j, and multiplying z to the j is the probability that x1 plus x2 equals j. So therefore, what I conclude is that the generating function, the product of the generating functions is equal to the generating function of the sum, which is just what I wrote here. Okay, now you're beginning to see the power of this thing, because the operation of convolution, that's what this is, convolution. A convolution is a sum of products. So a convolution is relatively complicated as opposed to the operation of multiplication if I'm working in transform space. So if I want to add two random variables and I have their transforms, in effect, I multiply the transforms. So that makes life very simple. Okay, so let me give an example of that. Let's go back to the original examples. Any questions before I erase this? Okay, suppose, so here's an example. Suppose Sn is equal to x1 plus x2 plus xn, where the xi's are iid, so they're independent, identically distributed, and the probability that xi is equal to 0 is equal to q, and the probability that xi is equal to 1 is equal to p, or 1 minus q. Okay, so what we have here is we have a sum of independent, identically distributed random variables, and those random variables are Bernoulli random variables because each one of them takes on values 0 or 1 with probabilities q and p. In fact, I could take the viewpoint that I could say, well, what I have here is I have a sequence of trials, and every trial is either a failure, a 0, or a 1, a success, like that, and there are n such trials. And so the sum of the values is the number of 1s. So the sum of a bunch of IID Bernoulli variables corresponds to the distribution of the number of successes, or the number of 1s I would get if I had a sequence of n independent trials. And of course, we can calculate that probability directly. Everybody knows what the answer is. It's a binomial distribution. Because if I said, what's the probability that the number of successes in a sequence of n independent trials, where the probability of a success, a 1, is p, and the probability of a failure, a 0, is q, you would say, well, let's see. Okay, what's the probability that Sn is equal to j? Well, you'd say, well, if I looked at that string, if I have exactly j 1s, then for any particular string with exactly j ones in it, the probability of that is p to the j times q to the n minus j. That's the probability for any string, any particular string, which is exactly j ones and n minus j zeros. And then I would say, OK, now what I have to do is I have to add up over all strings that correspond to all the different ways I can interleave the zeros and the ones. And how many such strings are there? Well, as everybody knows from elementary probability, that's given by the so-called binomial coefficient n choose j. That is, this is the total number of ways I can choose the positions, the j positions out of n that contain the ones. And that's the so-called binomial coefficient. So we know that's the answer. We know that by a combinatoric method. But suppose I didn't know that's the answer. Okay, now I obtain this by a combinatoric method, but now I want to recognize that, of course, that is exactly the same statistically as this is, and so I ought to be able to use my theorem about generating functions. OK, so I claim that the generating function of Sn evaluated at z must be equal to the generating function of each of the x's multiplied by itself. Of course, I proved the theorem only for the case in which we had only two x's, but obviously I can extend that to any number, any finite number of x's. OK, so what's the generating function of x1? Well, we know that x1 is a Bernoulli variable. We already did that. That was our first example. So its generating function is q plus pz. So that's the generating function of x1. But since they're identical, then x2 also has the same generating function. And in fact, each of them has the same generating function. So I multiply those things out. I get that thing raised to the nth power. OK, if that's the generating function, now all I have to do is expand that. But now I can expand that by the binomial theorem. So according to the binomial theorem, this would be the sum. So now I'm going to binomial theorem. So what I'm doing now is I'm doing arithmetic on the generating function. But the convolution part was easy. All I did was raise that thing to the nth power. And so what I would have is the sum as j runs from 0. Well, let's see. When I raise this to the nth power, what I would get would be n things taken j at a time, p z to the j, q to the n minus j, summed as j runs from 0 to n. That's the binomial expansion of that. And then I simply recognize that, OK, what I'll do then is I'll rewrite this by simply factoring out the z to the j. And so I see that what I have is a generating function that generates the binomial distribution. It generates exactly the same as what we had before by a different argument. And so what this shows officially then, formally, is that the probabilities for j running from 0 to n are given by those formulas. And for every j greater than n, the probability is 0. So there are only a finite number of terms in this infinite series. The coefficients of all the terms from n plus 1 on up are 0. Suppose I wanted to calculate the expected value of Sn. Well, if I did it from the definition, I would have to take the values the random variable takes, which I'm calling j, times the probability that it takes those values, n things taken j at a time, p to the j, q to the n minus j, and sum over all j. That's no big deal. I mean, well, it's sort of complicated. This is a standard exercise in elementary probability. But there's a better way to do it, or another way, or I don't know if it's better. It's not the best way. But A way to do it would be to simply calculate the derivative of the generating function and then set z equal to 1. So when I calculate the derivative, well, that's the generating function. So its derivative is n times q plus pz to the n minus 1 times the derivative of the thing inside, if I remember my freshman calculus, which is p. And then I set z equal to 1. And so when I set z equal to 1, the thing inside the parentheses becomes q plus p, which is 1. 1 raised to any power is 1, and I'm left with np. And of course, we already know that that is exactly what I would get if I went through the work of evaluating that sum. The expected value of a sum of a binomial random variable with parameters n and p is n times p. So it works. Now that's not the only way to do it, to find the expected value. In fact, the best way to find the expected value of something like this is to say the expected value of the sum is the sum of the expected values. And the expected value of each of the x's is simply p, and there are n of them, so the expected value of the sum is np. But I'm not doing this because I want to find the answer. I'm doing this to illustrate the way the theorems work. Okay, because soon you'll see that this allows you to do problems that you couldn't do in an easier fashion. Okay, let me give another example. Okay, suppose x1 is Poisson. So I'm just making up some notation here. x1 is Poisson with parameter a1, and x2 is Poisson with parameter a2. And they're independent. Okay, so what I want to do is I want to add up two independent Poisson random variables. So what I'll do is I'll find the generating function of the sum. Well, according to my theory, that's the generating function of the first one times the generating function of the second one. Now, we already figured out what the generating function was for a Poisson variable. That was our previous example. And so this is e to the minus a1 times 1 minus z. That's the generating function for the first one. Okay, generating function for the second one is exactly the same form, except that instead of a1, I have a2. But now by arithmetic, that's the same thing as e to the minus a1 plus a2 times 1 minus z. Okay, so this is by arithmetic. So what's my conclusion? My conclusion is that the generating function of the sum is of the form e to the minus something times 1 minus z. So therefore, it's a generating function for a Poisson whose parameter is the sum of the two parameters. Okay, so therefore, x1 plus x2 is distributed as a Poisson with parameter a1 plus a2. So I proved something important here very quickly, very easily. If I add up two Poisson variables and they're independent, then their superposition or their sum is again a Poisson random variable whose parameter is the sum of the parameters. Okay, but I didn't have to go through any convolution arguments. It was really easy. All I did was multiply the generating functions and then recognize that when I multiply those exponentials, I get something of this form, and that's the same form as the original. So what could be easier? Okay, so that's the power behind all of this. Let me make an observation here. One other observation about generating functions. The generating function of a random variable, x, is the sum of the probability that x equals j times z to the j, summed over all j. Now, if I wanted to, I could look at that formally as saying, well, that's the same thing as the expected value of z to the x power. That is, a generating function is an expected value. Because suppose I told you that I have this number z. Remember, the z is just a dummy variable. It doesn't really, has no physical significance. So I have this number z, and I'm raising it to the power of the random variable. So what's the expected value of that? Well, the expected value of the function is the value that the function takes, which is z raised to the various values that x takes, weighted by the probability that x takes those values, summed over all possible values. So formally speaking, a generating function is an expected value. OK, so from that, suppose I wanted to find the generating function of x1 plus x2. That's the same thing as the expected value of z to the x1 plus x2. But that's the same thing as the expected value of z to the x1 times z to the x2. But if x1 and x2 are independent, then obviously z to the x1 and z to the x2 are independent. Z is just a number. So by independence, if I assume independence, then the expected value of a product is the product of the expected values. So that gives me e z to the x1, e z, let's see. Everybody knows, if you ever take a course on how to teach, is that you don't write yourself into little tiny corners like that. OK, so let me take my time here and make a bigger corner. So this is going to be e of z to the x1 times e of z to the x2. But of course, since we've identified the generating function with the expected value, that's the same thing as the generating function of x1 times the generating function of x2. So that's another proof that the generating function of the sum is the product of the generating functions. Of course, this is deceptive. This is really easy, but it's easy because I've used the fact that I know from someplace else that the expected value of a product of independent random variables is the product of the expected values. So of course, to prove that, if I had to prove it, then I wouldn't have gained anything because that's requires some arithmetic that I'm ignoring here. Okay, but if that's one of the things that's in your repertoire, then this proof is just an observation. Okay, so that's generating functions. And generating functions are used in several ways. One of those ways is that you write equations which represent the relationships of probabilities with respect to each other, and then you multiply through by z to the j and sum. And then the end result is what you get is another equation, which is generally a simpler equation for the generating function. So instead of having equations for the individual probabilities, then you have an equation which is generally an infinite number of equations, each for for one of the probabilities. Instead, you transform that into a single functional equation for the generating function. And sometimes that functional equation is easier to solve, and sometimes even if it isn't, it's easier to get information out of it by differentiating through implicitly and then being able to solve for the expected value in the moments. Let's see, I should write down the formula for the second moment here. This is left as an exercise in the book. It's equation 4.8. I won't go through the arithmetic. This is 4.8 on page 28. It says that the variance of a random variable is equal to, let's see, it was the second derivative of the generating function evaluated at 1 plus the first derivative evaluated at 1 minus the first derivative evaluated at 1 squared, if I copied this right. Okay, now, the way you verify that that's true is you just use the fact that you know that the variance of a random variable is the expected value of the square of the random variable minus the square of the expected value. Well, this term is that term, obviously. So all you have to do is show by arithmetic, by simply expanding this, taking the derivative and setting z equal to 1, and combining those two terms, that it comes out to be exactly the definition of the expected value of the square. So in other words, using generating functions, that piece is the second moment, and this piece right here, before I square it, is the first moment. And similarly, I can calculate all of the other moments. Okay, are there any questions about that? Okay, let's look at exercise number 4 on page 30. Compound distributions. Okay, so now, of course, the solution is in the solutions manual, so I'm not going to go through a lot of work here. So we have exercise 4, which is on page 30. And there it says, suppose that Sn, cap n, is equal to a sum, x1 plus x cap n, where the x's are IID independent, and in particular, the n itself is a random variable. All right, that's why I used the cap n there. So I have a sum of a random number of random variables. This kind of thing often occurs in applied probability and in queuing theory. Okay, now suppose that let's see. Okay, suppose that one of them has, let's say that the x's have generating function f. So suppose that the x's have PGF f, and the n has PGF, let's see, what did I call it in the book? G. So let's let h of z be the generating function of Sn. So h of z is the probability that Sn is equal to j times z to the j summed over all j. Okay? All right, now the next step is to say, okay, let's expand things. So that's the sum of j, and this is going to be the probability that x1 plus x2 plus x cap n is equal to j times z to the j. Okay, but now, what's this probability in here? I'm going to write the probability inside as the probability that x1 plus and so forth plus xn is equal to j given big N is equal to I times the probability that big N is equal to I, okay, summed over all I. And I still have my z to the j. So what I did was I replaced that probability by the sum of these conditional probabilities by the theorem of total probability. The probability that the sum of these n variables equals j is the probability sum equals j if the number of variables is I times the probability the number of variables is I summed over all I. So this piece is replaced by that. Okay, so what's the next step? Let's see. What do I want to do? Why don't I take the probability, let's see. Okay, what do I want to do here? I want to interchange these summation signs somehow, right? So I'm going to take, let's see, here I have the sum over I. Let's see, here I've got z to the j. I know what I want to do. Let's write this as the sum over j of the sum over I of the probability that x1 plus x little n is equal to j, except this is little I here now, times the probability that n equals I times z to the j. So all I did was take this conditional probability and say, since I know that the number of terms in the sum is I, I'll replace that index capital N by I. Okay, now I'm going to take this summation z to the j and move it in here. And I'll take this z to the j and move it in here. And so what I'll have is the sum over j of the probability that the sum of the x's is equal to j times z to the j. Okay, maybe I should rewrite that since I'm going to move to another board. Don't want to get too confusing. So we have the sum over I. That's this guy right here. And then we have inside the sum over j. That's this guy. Then I have the probability that x1 plus x sub I is equal to j. That's this guy right here, times z to the j. That's that guy, times the probability that n is equal to I. And now let's look at that piece in there. What is that? Well, that's the generating function of the sum of I independent random variables, because it's the probability that x1 plus and so forth up through xi is equal to j times z to the j. But we already have a theorem that says that the generating function of the sum is the product of the generating functions. So the thing that fits inside is the generating function of the x's raised to the ith power, because there's I of them. Okay, the x's have generating function f, so that thing in there is f of z raised to the ith power. And that is inside the sum over I multiplied by the probability that n is equal to I. But what is that? Well, this has got the sum over I of the probability that n equals I. Remember, I here runs from 0 to infinity, times something raised to the ith power. So this thing here is the generating function of n. What's the generating function of n? It's g. Except that instead of evaluating g at z, I've evaluated it g at f of z. Okay, so we have this really neat looking result. We just proved the following. We said that suppose we have a sum of IID random variables in which the number in the sum is itself a random variable. This is called a compound sum. And assume that the components of the sum have generating function f, and the number in the sum has generating function g. Then the generating function of the distribution of the sum is equal to the generating function of n, the number in the sum, evaluated at the generating function of f, the generating function of the components of the sum. Okay, so all of this kind of folds up into something that's very neat. For example, suppose now I wanted to calculate the expected value of Sn. Well, that would be h of z, h prime of z, evaluated at z equals 1. Okay, so now this stuff starts testing you on your freshman calculus, which I'm not very good at. Let's see if I remember it. Okay, but if I want to, I'm going to have to use the chain rule to differentiate because I have a function of a function. So if I differentiate, I get what? I get the derivative of f. Let's say I take the inside derivative, which is f prime of z, and then multiply it by the derivative of the function. Okay, did I do that right? Is that correct? Is that the right way to use the chain rule? Okay, and remember that this has to be evaluated at z equals 1. So what does that give me? That gives me f prime of 1 times g prime of f of 1. That's f prime of 1 times g prime of, now what's f of 1? Well, f of 1 is 1, because any generating function evaluated at 1 is 1. That just says that the probabilities sum to 1. Now, since f is the generating function of x, that's the expected value of the x's. And since g is the generating function of n, that's the expected value of n. And so we get the answer that we already knew. This is just an example, an exercise, checking things out, that says the expected value of a sum of IID random variables where n is the random number of x's in the sum is equal to the expected value of the x's multiplied by the expected value of the number of x's that there are. So this is exactly what you would have written down by common sense if someone said you had to make a guess. Okay, so everything works out, but notice that how, in a sense, how neat the arithmetic is and how you're actually using things from freshman calculus, maybe for the first time, because you actually want to find out the answer rather than because it's some exercise that somebody just gave you to give you a test. Okay, let me calculate from this something that I couldn't have gotten that easily. Suppose I want to get the variance of Sn. Well, now I just apply the formula. Now it gets messy, but it's straightforward. I simply differentiate through again, and then I use the formula that I had on the board before. Okay, I'm not going to write it down. I'm not going to do it. I'm just going to write down what the answer is, which is given in Part B on exercise number 4, and you can look it up in the solutions manual. Okay, the answer is, well, first of all, I take the variance of the x's, and I multiply that variance by the expected number of x's that there are. That's sort of common sense. You would expect that term. But then there's a second term, which is the second moment. No, it's the square of the expected value of the x's times the variance of n. So the variance of this compound sum is equal to the variance of each term times the average or expected number of terms. But then over here we have another term, which is the variance of the number of terms in the sum times the square of the expected value of the individual terms. So for example, if the number in the sum were a constant, which is the usual case, an ordinary sum, then this term would be 0. The variance would be 0, and you would get exactly the answer that you would expect to get, which would be that the variance of the sum is the sum of the variances. The variance of each of them times the number of them. But the variation, the variance in the number in the sum itself comes into the formula here, and this is just easy to prove simply by taking this thing and differentiating twice. Okay, so everything works out. Everything fits together like that. Very neat. Okay, that's exercise number 4, compound distributions. We're gonna use something like that shortly. Okay, so now I've covered the stuff, the elementary stuff on generating functions for discrete integer valued, non-negative integer valued random variables. And now let's get back to where we started, or we left off last time, which had to do with continuous random variables and Laplace transforms. So any questions up to this point? Okay, so now let's look at Laplace transforms, which starts on page 197. Now Laplace transforms page 197, are in fact a simple generalization of the idea of generating function, except that generating functions work only for discrete, non-negative, integer-valued random variables, whereas Laplace transforms work for random variables that are not necessarily discrete. In fact, Laplace transforms work for non-negative random variables, but with arbitrary distribution function, discrete, continuous, or mixed. Okay, so here's the definition. Suppose I have a random variable x, and it has a distribution function capital F. So the way I compute the Laplace transform is I take the differential of that, I multiply that by e to the minus st, and I integrate as t runs from 0. I'll write it as 0 minus because I want to make sure that I include the origin in the integration, to infinity. That's the definition of the Laplace transform of the distribution function of the random variable x. And let's call that phi of s. I'll put the x in here to indicate that we're talking about the transform of the distribution function of the random variable x. Okay, so note what I have here is that, again, I have the same idea as I had with the generating function, which is that I have this probability information here, and then I multiply it by something and add up. Add up, in this case, integrates. And when I get done, whereas I originally had a function of t, or in the other case, a function of the integers j, I come back with another function of a dummy variable which earlier was called z and now traditionally is called s. So what this thing does is you tell me what this is, and I transform that into another function. And whatever information was in here is now in here, except it's in a different form. And furthermore, there are theorems which say, again, we're going to ignore the analysis aspect of it, that say that under certain conditions, which we'll assume are true, we'll worry about these details as we go along, if you tell me what the phi is, if you tell me this function, not a number, but if you tell me its functional values for all s, or for a sufficiently dense set of s, if you tell me this, this side, then that uniquely determines the function that produces it. So I can go backwards. Now, I have some properties here, just like with ordinary generating functions. For example, phi of 0, well, if I put a 0 in here, that would make the integrand 1. And I would be integrating the distribution function from 0 to infinity. So phi of 0 is going to be 1. Okay, so that's one of its properties. That's a normalization property. That's equivalent to the one that said g of 1 is equal to 1. It's not exactly the same thing, but it's analogous. And we'll see that the generating function actually comes out of this as a special case. All right, here's another one. Suppose that I took the derivative phi prime of s. Well, if I differentiated this formally, again, now we have an integral. It's an infinite integral, but the integrand is well behaved. It doesn't oscillate. It's bounded. Never negative. All kinds of good stuff. So this is nice and simple, and this is a well-behaved function because this is a distribution function. So again, it doesn't oscillate, and it varies between 0 and 1. So everything here is well-behaved. So if I want to differentiate this, then I just say, OK, I can interchange the order of differentiation and integration, all of those rules that in applied mathematics that in physics you assume are OK, but in mathematics that's what it's all about, is proving that that's OK. So if I differentiate this, then I would get minus the integral from 0 to infinity of, now I'm differentiating with respect to s. So I have t e to the minus st df of t. And now, if I set the value of s equal to 0, analogous in the generating function to setting z equal to 1, then what I would get would be minus the integral from 0 to infinity of t. Now, when s is equal to 0, e to the minus st is 1, and I have t df of t. But of course, I recognize that as exactly the definition of the expected value of the random variable x. So that's e of x. So just like with the generating function, the expected value of the random variable x, if it did have a generating function, if it was non-negative integer valued random variable, was the generating function, derivative evaluated at 1. So with a Laplace transform, if I take the derivative of the transform and evaluate it at 0, I get the expected value. Same idea. That is, if I have the transform, I can find the mean value by taking a derivative. In fact, it's easier if I have Laplace transforms to get the second moment. Phi double prime evaluated at 0. Okay, what would that be? Well, if I differentiated this twice, then I would get, if I differentiate it the first time, I get a t down here. Remember, I'm differentiating with respect to s. Differentiating it again, I'm going to get another t. So I would have here the integral from 0 to infinity of t squared e to the minus st d f of t. The minus sign has now canceled itself when I differentiate it twice. So you see every time I differentiate, the signs alternate. And if I then evaluated this at s equals 0 to get that, then I see that the e to the minus st is simply 1, and I'm left with the integral of t squared dfx of t, which of course you recognize as being the expected value of x squared, or the second moment of x. If I differentiate again, then I would get the third moment with a minus sign. And again, the fourth moment, and so on. OK, so everything is the same. Well, analogous. Now, the interesting theorem, which I'm going to state now, and I won't have time to prove, but we'll talk about it later. So let me do it right here. And it's obvious. If x1 and x2 are independent, then the Laplace-Dirichlet transform of x1 plus x2, the sum, is equal to the product of the Laplace-Dirichlet transform of x1 times the Laplace-Dirichlet transform of x2. So now, instead of having to form an integral convolution, I just multiply the transforms. OK? OK, so we'll start there next time. Let's see, one more statement I want to make is 6.2 before we quit, and say this. Phi of s is, by definition, the integral of e to the minus st df of t, where f is the distribution function. Now, suppose that f happens to be differentiable. Then this would be the integral of e to the minus st, let's call the derivative little f, as we often do, dt. Now, those of you who are double E's or physicists will probably recognize this thing as the definition of the Laplace transform of f. So the way you calculate the Laplace transform of a function is you take the function, you multiply it by e to the minus st, and then you integrate it. So what this says is that the Laplace-Dirichlet transform of some function is equal to the Laplace transform of the derivative of that function, if there is a derivative. In particular, if the random variable has a density, then the Laplace-Dirichlet transform of the distribution function is equal to the Laplace transform of the density function. But if the random variable does not have a density, even though this part doesn't exist, this can still be evaluated, and all of our theorems still hold. OK, we'll continue with this next time, and you'll see how all this fits into queuing theory.